Hello, everyone. This is our atoms and periodic trends review guide. Okay, basically, what if you're watching this? I wanted it to kind of go over again our review guide. Okay, um, odds are we didn't do very well on our test, and that's okay. The thing is what we're do good at is being able to bounce back, and that's what we're just going to do. So odds are I'd probably talk to you about our class data. Okay. If that's the case, that's totally fine. And what we're going to do now is we are going to learn and we're going to redo this because what we need to do is we need to set ourselves up to be successful. Okay. So what I wanted to do is I wanted to make a video just in case if I wasn't there and able to teach it. So here is what we're going to do. This is recorded on my iPad. I will upload this and you will be able to watch it whenever, but hopefully this will be um, good enough for us to get to where we need to for our current unit here. Okay, so alrighty, let's get started. So number one, it says electrons in the outermost orbital of an atom are called what? Okay, so we have different kinds of electrons. All right, if I draw the Lewis dot structure, let's say for lithium, which is element number 3 on your periodic table, what's going to happen here is this: if this is my Bohr model, what I have is 3 electrons. I got 1 and 2. Okay. And then my third one is going to go on the outermost orbital here. Okay. Now, these electrons that are on the outermost orbitals, these guys are important, okay, because this is where all of our chemical reactions occur. So even though we have 3 electrons, it doesn't necessarily matter because the most important ones right now are the ones that are on the outside, which is our valence electrons, which is these guys right out here. So these ones are called our valence electrons. Okay, valence electrons are the ones that are on the outermost orbital of an atom. Okay, so electrons in the outermost orbital of an atom are called what? These are called valence electrons. Okay. Another way, if you are unsure, if you don't want to spend a lot of time drawing Bohr models over and over and over again, it's totally understandable. Okay, there's actually a shortcut for us to figure out where these valence electrons are located at as well, and that is on your periodic table. Okay, so here is your periodic table. Okay, you should have one either on a blue sheet of paper or a white sheet of paper. It looks very similar to this, okay, except mine just has color to it, okay? So, when we talked about lithium, okay, lithium is all the way over here in our second period, all right? This thing here that it's in, this is called an element square, okay? Lithium is in its element square. So, the important thing here that we need to know is that um, what it's in currently, it's not only in its element square, which I just boxed in, but it's in what it's called a group. Okay, so a group is a vertical column. Okay, your group vertical columns, if you're unsure, which is totally fine. These are the guys that go up and down. All right, so your whole group is going to be all of column number 1, okay? So here we have a 1, all right? So all of these here, these guys are all part of your group 1 elements, okay? So why is that important? Well, group 1 elements, what they tell you is, or the group number in general, what they tell you is how many valence electrons are present in that element, okay? So if lithium here is in group number 1, okay, that means it has one valence electron. So if any of these elements that are in group 1, so hydrogen, sodium, potassium, rubidium, cesium, and francium, they are all going to have one valence electron because it's in group 1. Okay. So what else that means is that if we have a 2 here, if we scroll over, we have a 3, 4, 5, 6, 7, and 8. Okay. So all the ones that I just circled, these are known as your group numbers. Okay. And your group numbers, what they tell you is how many valence electrons there are in an orbital of an atom. Okay. So we got our group numbers. Our group numbers tell us how many valence electrons. Okay. So let's take care of that for now. All right. Now going back to our study guide here. Oh, perfect. Here it says elements in the same vertical column, okay, which we literally just talked about, are called what? These here are called our groups. Okay. Your groups, remember, they're vertical, so they're going up and down. Okay. All right, next is number 3. Elements in the same horizontal row, okay, horizontal row are called what? So if you aren't sure what horizontal means, that's totally fine. Because here, inside the word horizontal, we have a special word, okay? And this special word, if you look closely, if we take it apart here, it says horizon, right? So if any of you guys have ever seen like a sunset or the sunrise and you're looking all the way far out, right? And you're looking from left to right, that is called the horizon, okay? So horizontal row means from left and to right, okay? So now we have these things. What are these horizontal rows called on the periodic table? So if we go back to our periodic table, you will see these things over here are called periods. Okay. Now, each period is located on this left side here. All right. This period tells you a few things. All right. The period is your horizontal row. So all the elements that are in that period are part of that row. Okay. So that means we have hydrogen over here is in the same horizontal row as our helium over here. Okay. They're all part of the same period. Okay. What that also means is that period 2, okay, we have period 2, lithium and beryllium, these guys, they are also part of the same row over here, the same period as these ones guys over here. Okay. So the other thing that you need to know about periods, okay, your period tells you which orbital it is when you're filling out your Bohr models. Okay, so for example, period 1 is your first orbital. Okay, so if you're looking at period 1 here, you want to look and see, all right, we have hydrogen and we also have helium over here. Okay, now the question normally comes to, all right, well, how many electrons can you fill in these periods? Okay. In your first period, you can only fill in 2 electrons. Okay. The reason we can only fill in 2 electrons is because we only have 1 box, 2 boxes available. Okay. So we're not counting the atomic number. We're just think of it as just counting the boxes that are present. Okay. So if that's the case, then we would only have, if we're counting the boxes in period 2 in our second orbital, okay, I got 1, 2, 3, 4, 5, 6, 7, 8. Okay, so if you're unsure, let me show you again. I got 1, 2, 3, 4, 5, 6, 7, and 8. Okay, those tell you that you have 8 boxes, so you can only fit in 8 valence, or sorry, not valence, 8 electrons in the second orbital. Okay, because we only have 8 spots. One second. We only have 8 electrons or 8 boxes present, so we can only fit that many in there. So if you're looking at it, okay, if you notice, oh, look, period 3 is exactly the same size as and has the same amount of boxes as period 2. So period 3 would also can only fit 8 electrons as well. Okay. So in the next case, if we were to go to period 4, all right, period 4, which we're not going to get into, that's be like higher level chemistry. If you're interested in it, then yeah, we would get into it. But in this case, since it's just physical science, we're not going to get into it. But for period 4, okay, because we would start here at potassium, we would also, all of these elements here, okay, all of those guys, those could be included in an orbital. So how many electrons you could fit in there. Okay, but for our sake, we're just going to be focusing on the first 3 periods. Maybe we might dip our toes in for potassium and calcium only, but that would be the most. Okay. So let's go back to here. So our horizontal row are called periods. All right, these horizontal rows are periods, so they're going from left to right, going across the periodic table. Okay. So number 4, what charge does a proton have? All right, so we're talking about protons. Protons, that prefix pro, you guessed it, means positive. So protons are positive charges. Okay, as a positive plus charge. What charge does an electron have? Okay, so this part I've seen on our tests and our quizzes that a lot of times we get this confused. Okay, but remember, electrons are going to have a negative charge. Okay, so the minus sign is what we use. All right. So if that has a negative charge, then what charge does a neutron have? Okay, a neutron charge, all right, is going to have a neutral charge. Okay, if you're unsure what that means, all right, think of it as if you are ever driving a vehicle or a car or anything like that. If you give it gas and it's in neutral, the car is just going to rev and it's not going to move. Okay, so neutral is just another way for us to say no charge. Okay, so no charge, nothing's really going to happen. So, why do we say neutral when it's so much easier to say no charge? Well, the reasoning why we are saying that is because it's much easier to remember. Neutrons are neutral because our first 5 letters of neutron and the first 5 letters of neutral are exactly the same. Okay, so if you are able to remember that a proton is positive, right? So protons are positive, neutrons are neutral, okay, then you should be able to figure out by process of elimination that electrons are negative charge. Okay, so now what we have here is number 7. What is the center of an atom called? Right? So the key word here is center. Okay. Now, when we're talking about a center, you guys have heard this word before, and you heard it in biology as well. Okay. What is the center of a cell called? All right. If you guessed nucleus, you're correct. So it's the same thing with here in our atoms. So the center of an atom is called a nucleus. Okay. The nucleus is the center part of our atom, just like how it is the center part of our the nucleus is the center part of our atom, just like how you learned it is the nucleus is the center part of a cell in biology. Okay. So now, number 8, the rings around the atom are called. So if we have, let's say, let's do another lithium guy here, another lithium Bohr model. Got 1, 2, 3. Okay. These rings, those rings, that's what they're talking about. This is called an orbital. Okay. An orbital. If you're unsure what an orbital does, think of it as like this. Okay. An orbital, when something is orbiting something else, right? That means it's going around and around. Okay. So think of it as the moon is orbiting the Earth, and the Earth is orbiting the sun. Okay. So our electrons, these guys here, these electrons, they are orbiting our nucleus. So they are orbiting the nucleus in the center here. Okay. And the rings that we're calling them, that's where they're most likely located, are called orbitals because those electrons keep going around and around our nucleus of our atom. Okay. All right. Our next part here, number 9. Number 9, it says, what does the atomic number stand for? Okay. Now the key word here is atomic number. All right. So think of it as what subatomic particle gives the atom its identity. Okay. So think of it as, so let's go back to our periodic table before we get into that. All right. Now we're going to look into nitrogen here. So here is nitrogen. Okay. And I boxed it in its element square. Now we have a bunch of information that's being shown inside this element square here. Okay. So we have numbers, we have a letter, we have a word, and we have another number that has a decimal point in it. Okay. So what I'm going to do is I'm going to label this for you so we're all kind of on the same page here. Okay. So here, this number 7. Okay. This number 7 is your atomic number. Okay. So atomic number. Your atomic number tells you quite a bit of information. All right. First of all, your atomic number is your identity part of your atom. So when I said which subatomic particle gives you the identity of the atom, I am specifically talking about the subatomic particle known as protons. Okay, so the number of protons gives the identity of our atom or the identity of our element. Okay, so if we were happen to change the number of protons, let's say we were to add one, it would no longer be nitrogen, but then it would be oxygen instead. Okay, if we were to take away a proton from nitrogen, it would no longer be nitrogen, it would be considered carbon. Okay. So protons, the number of protons, it tells you what the element is. Okay. Now the other thing that the atomic number tells you. And since these are all neutral atoms, okay, what neutral atoms means is we have the same number of protons and electrons. Um, that's what's happening here. So our atomic number not only tells you how many protons, but also how many electrons as well. Okay, so protons and electrons. So in order for this to be electrically neutral, we would need to have 7 protons and 7 electrons for those charges to cancel each other out. Okay. Now here, the next thing that we have is this letter N. Okay, this letter N is known as our, I'll draw it over here, element symbol. All right. Your element symbol is just a simplified version of the word. So scientists they think really fast, but they're also lazy and efficient. So they want to shorten things up as much as they possibly can. So what they decide to do is they give things symbols. So this is nitrogen. This N stands for nitrogen. Okay. And here is the word nitrogen below. Okay. Now, the last thing here, this guy, this 14.01, okay, this here also tells you quite a bit of information as well. This 14.01, or what we'll do in our case is just round it to 14. This here tells you your atomic mass. All right, your atomic mass. All right, your atomic mass is made up of 2 subatomic particles. Okay, and these 2 subatomic particles are located in the nucleus. All right, your atomic mass is a total. All right, so I would really remember that that part is a total. Okay, so the 14 is a total. All right. It is a total number of how many protons and neutrons that are in the nucleus of our nitrogen atom. Okay. So if I wanted to figure out how many neutrons I have, well, before I get into that, let me just write this down. So atomic mass is your total, and it tells you how many protons plus neutrons. Okay. So if I wanted to figure out how many neutrons I have, let me erase this, it's kind of messy. All right, neutrons. What I need to do, if I want to figure out how many neutrons, I would need to take my atomic mass number. Okay, so you would take your atomic mass number. So if you weren't paying attention, I would really paying attention now because on your test, this part, a lot of us on our test got this wrong. Okay, because this is how you figure out on your Bohr models, which we'll get to later, how many neutrons we need to put in. So if you take your atomic mass, okay, so in this case, our atomic mass is 14, and if we subtract it from our atomic number, 7, this will tell you how many neutrons we have. So 14 minus 7 gives us 7 neutrons. Okay, 7 neutrons. So here, this little box can give you so much information. It tells you how many protons it has. It tells you how many electrons it has. It also tells you how many protons and neutrons are added together. So if you are drawing your Bohr model, all right, so your Bohr model is that picture of the atom that has all the rings on it. If you are drawing that and your Bohr model does not equal the atomic mass, so if your protons and neutrons, when added up, if they do not equal 14 in the center part, that means you did it wrong, okay? And we will get into that later here in the video. All right, so we're going to move on to our next part here. Going back all the way back to number 9. So what does the atomic number stand for? The atomic number stands for, oops, the total number of protons and electrons in a neutral atom. Okay, and if you can't read my handwriting, I apologize. There will be a typed version in Google Classroom for you guys as well. Okay. So, what subatomic particles count for atomic mass? Okay, so this word subatomic particles, so subatomic here. What we need to do is we need to break this down into a little bit of parts. Okay, so our first part here we need to look at is this prefix sub. Okay, so sub, when you hear the word sub, you want to think of like a submarine. Okay, a submarine, remember, a submarine goes under water, right? Sub means under, marine means water. So if we're talking about subatomic particles, okay, so subatomic, we have parts that are below an atom. Okay, that means we're breaking apart our atom into smaller particles. So what this is asking for, the subatomic, is your protons, neutrons, and electrons. Okay, this isn't the answer. All right, I make that very clear. I'm just telling you and I'm helping you identify that this here, when you see the word subatomic particles, that's what it's asking about. So, what subatomic particles? So, what particles count for atomic mass? Okay, so in this case, there are two subatomic particles. Okay, and the only two particles that we're going to count for, these two are located in the nucleus. All right, so if you guessed it, they are protons and neutrons. Okay, we do not count electrons in our atomic mass, okay, for a few reasons. So the first reason is that electrons are so incredibly tiny, they're much smaller than even protons and neutrons, that they don't even bother to account it towards the mass. That's the first part, okay? Now the second reason is that our electrons are moving so fast and that they're orbiting or going around our nucleus and that they're not in the same consistent spot. And they're also being traded and given away and shared that the scientists decided not to account electrons towards atomic mass. Okay, so atomic mass here is only talking about these two guys, your protons and your neutrons that are located in the nucleus, okay, in the center of your atom. So, number 11, what needs to be the same in order to have a neutral atom? Okay, so now this is not talking about which subatomic particle is neutral. It's talking about how can we have a neutral atom? Okay, so we need to have two subatomic particles that need to be there in order to cancel each other out. This means we need to have same number of protons and electrons. Okay, so in order for our atoms to be electrically neutral, okay, they have to have the same number of protons. So they have to have the same number of pluses and the same number of minuses. Okay, think of it as if you have $3, right, and you buy a candy bar that costs also $3. Okay, well, you end up with zero or neutral or nothing, right? So that's what it's talking about. When you bring it down, you need to have the same number of protons and electrons. That's why when we're looking at our periodic table, the atomic number, right? The atomic number tells you how many protons and electrons are in a neutral atom. Okay? So, what increases when we move from one period to the next? So remember, your periods, okay, your periods here are talking about your rows on the periodic table. So what increases when we move from one period to the next? So that is where we are going to get into our packet, the packet of, you can call it notes, you can call it a tool, whatever you want to call it, but it's not work, so don't worry. It's theirs as a resource to help you figure out and identify these different kinds of trends. Okay, so what a trend is, it's talking about an overall pattern that is happening or occurring. Okay, that doesn't mean that a trend is always going to be consistent all the way through, but if we start low on one end and we end up high on the other, the overall trend that it's going to be increasing. Okay, so let's take a look at one of our periodic trends here. So this one is called electronegativity. All right, we aren't going to get into this one quite yet. On the back of this page is also the same thing, except it's a little bit better. The difference between these two is that this has number values, right? So think of it as fluorine, which is this bright red one over here, is 4.1 times likely to try to take an electron versus these guys over here that's at 0.9. So, okay. So this one is the same thing, but now the difference is that we have this column right here, our noble gases, and we'll get into that in a moment. Ionization energy. So ionization energy we'll also get into a little bit later, but it's different from electronegativity. Here's another picture of ionization energy. Now, this is the one that we need to talk about, okay? So the question is, what increases when we go from one period to the next? So if you remember that here is period 1, period 2, period 3, period 4, 5, and 6, okay? These are showing you the different rows, okay? So what increases when you're going from the left to the right, all right? This gets a little tricky because it feels a little bit deceiving. So one thing that we can notice as we're going from the left to the right is that our atomic number, so see where it says 27, 28, 29, and 30, okay? Those are your atomic numbers. Your atomic numbers are increasing when you're moving from left to right. Okay, so when you're moving from left to the right, they're increasing. The atomic numbers are here. Okay, but that's not really what I want you to focus on here. All right. When we're going from one period to the next, we want to look at the size of the radius. Okay, so if you're unsure of what a radius means, that's okay. Okay, your math teachers will get into it in a little bit later when you're talking about circles. So let's see if I can draw a circle. The power of technology. So what we have here is a circle. Okay. So when you have from one edge of your circle to the other side, okay, if it's that's I don't it might be close to even. It doesn't look like it. Well, anyways, so from one edge all the way to the other side, okay, that is called your diameter. Okay. Now, what a radius is talking about the center point, okay, all the way to the edge. That is a radius. All right. So, what atomic radius is talking about is the size of our atoms. Okay. So, what we have here is that we have a different size of atomic radius. All right. And our smallest one is our friend helium, all the way over here in the top right. Okay. And our largest one over here, at least on this picture, is our cesium, which is all the way here in the bottom left. Okay. So now what I want you to look at is helium right here is element number 2. When we add another orbital, we have to move down one period, right? So we're going from one period now to period 2. Okay. When we're moving down a period, what we're also doing is adding another orbital, okay? So we, instead of period 1 is just one orbital. So 1 is period 1. Period 2 would means we are adding a second orbital, okay? Now, what we have here is when we add a second orbital, that means we're making more space, okay? So we're making more space. When we make more space, we're allowing for more rooms for protons, neutrons, and electrons, okay? So look at the size difference between our helium, that's the little tiny dot way over here, the size of helium, versus the much larger ball of lithium. Okay, and that's just simply by going down one singular row. Okay, so we're going to go back to here. Okay, what increases when we move from one period to the next? This, what increases is the orbits or the orbitals and atomic radius. Okay. All right. So, number 13, it says how many electrons can fit in each of the 3 periods. So this is not asking for the total amount of electrons. So if you go to your periodic table, okay, we already started writing it down. So it depends on what period it is in. So for example, we have, period 1, which is over here, period 1, we have 1, 2 elements in our first period, in our first row here, okay? So that means this side has 2 electrons that we can fit in our periodic table, all right? In our second period, which is here, we got 1, 2, 3, 4, 5, 6, 7, and 8, okay? 8 boxes, that means we can fit 8 electrons in it. Now, if we look at our third period, it's the same thing. So that means we got 1, 2, 3, 4, 5, 6, 7, and 8. So again, we can fit 8 electrons in our third period or a third orbital. Okay. So how many electrons can fit in each of the 3 periods? So you can fit 2, then you can fit 8, then you can fit 8. Okay. So 2, 8, and 8 for a total of 18, which gets us all the way to argon, I believe. All right, so for 14, what I would do if I were you, I would circle it, I would star it, I would put like a smiley face next to it, I don't know, or a sad face, if that's just the mood for the day. But you know what? We're happy. We're happy because we're in school. Yay! So, what we're going to do instead is for 14, the reason why I'm saying this is because this question is not only going to be on your test, this test, It's also going to be word for word on your test for the chemical reactions unit, which is our next unit. So the question is, what is the octet rule and why is it important? Okay. Now, the key part here is talking about this oct. Okay. So, in order to help you remember what octet means, okay, how many legs does an octopus have? Well, an octopus has 8 legs, right? So in this case, we aren't talking about legs here, we're talking about electrons, all right? So the octet rule is saying that atoms prefer to have 8 valence electrons in the outermost orbital. Why? To be stable. So atoms prefer to have 8 valence electrons in the outermost orbital to be stable. So your why is they want to be stable, okay? So atoms prefer to have 8 valence electrons in the outermost orbital. So they want to have 8 on the farthest orbital possible, right? The valence shell. Why? To be stable. So that's why our atoms form bonds. They form chemical reactions. Because these guys, what they want to do is they want to become stable. So our next part here, it says, what does a Lewis dot structure show us? So a Lewis dot structure shows us the valence electrons of an atom only. Okay, I double underlined only, okay, because that's what is most important as of right now, what we're going to be talking about, especially in our next unit, about our chemical reactions here, okay? So if you draw, let's say, fluorine, which is element number 9, but it's in group 7, fluorine is F. Since it's in group 7, it's going to have 7 valence electrons that look something like this. Okay, this here is a Lewis dot structure. Okay, so what is the difference between a Bohr model and a Lewis dot structure? So we got Bohr models show protons, neutrons, electrons, and our orbitals. Okay, so it's more intricate. There's more stuff that's going on with the Bohr models. It takes a lot more time. So, but Lewis dot structures only show a valence electrons only. Okay, so that's the key difference here. All right, valence electrons, Lewis dots only show you your valence electrons, whereas the Bohr model shows you everything, right? So we were talking about, like, we'll get into it later in here. But you have like protons, neutrons, and you got a bunch of circles that looks like this, which is our orbitals, right? And if let's say if we're doing fluorine, okay, which is element number 9, so that means we got 9 protons, and I believe the mass is 19, so we would have 10 neutrons here. We would also then fill in our orbitals. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons. Okay. You know, here is your Bohr model. Okay. So your Bohr model, if you did it correctly, okay, it does show your valence electrons as well. Okay. If you did it correctly, your valence electrons from your Bohr model are right here. These guys. Now, if you look over here, we have these ones as well. Those are your valence electrons. All of them. Okay. All right. What is the difference between a cation and anion, and why do atoms want to gain or lose electrons in the outer orbital? Okay. So a cation, I know some of you guys don't know, but here we have a cation, right? And here we have the word cat. So I know many of you guys don't know me as I am right now as a strange man that's coming from the voice inside of this video. But here we have a cat, right? Personally, I love cats. I have 4 cats myself, and I love them, right? And they make you feel good, make you feel warm and fuzzy, even positive, even, right? So a cation, right? A cation here is a positive ion. Okay, we got the word cat in here. Oh, it's my wonderful drawing of a cat. Please don't make fun of me. So we have our cation, right? It's supposed to be happy. Yay. So a cation is a positive ion. Okay. Then we have something called an anion. All right. And one of you brilliant young scholars from Mr. Bloomfield's class, Mr. Bloomfield was actually very excited and told me all about it, about how can you remember what an anion is. Okay. So an anion, as someone once mentioned, so we have an ion is the same thing as a, n is negative, and then we have ion. So anion is a negative ion. Okay. Well, that's all fine and dandy, but what the heck in the world is an ion? All right. So what we have going on here is when we have our neutral atom. Okay. So since we got fluorine here, fluorine in its neutral state, okay, that means it has the same number of protons and electrons. So it has 9 protons. Let me write it out. Protons and 9 electrons. The number of protons and the number of electrons cancel each other out, making it a neutral atom. Okay. Now, when we draw the Lewis dot structure like this, fluorine is going to need only one more electron for it to become stable and it to be just like its noble gases that are so fancy That's all they really want, right? That's all what our atoms really want is just to be stable. So what it's going to do is it's going to eventually form a bond and connect with itself right here with our solo guy. Okay. Now, when that happens, our numbers change. So we still have 9 protons, but now since we gained an electron, this turns into 10 electrons. Okay. So when we gain electrons, this turns in, so gain electrons turns this neutral atom is no longer an neutral atom. It's now a negative ion or an anion. Okay. If it's going to lose electrons, so let's say our sodium here. Hold on, let me move this. Move it down there. That'll be fine. So if I have a sodium atom, okay, sodium has 11 protons and 11 electrons in a neutral atom. It's in our group 1 element, so that means we have 1 valence electron. Now, our metals, okay, our group 1, our group 2, and our group 3 metals, those guys, they're going to want to get rid of their electrons. They don't want them. Because when they get rid of their electrons, it allows them to fall back into their stable orbital from before. Okay, so let's say it gets rid of that electron. Poof, it's gone. All right, that's no longer there. So that means our numbers also change. So instead of 10 or 11 electrons, we now move to 10 electrons. We lose one. Okay, if we lose one, that means now we have more protons that are positive. If we have more protons that are positive, this is now a cation. Okay, cation. So hopefully that makes sense. If you're unsure, just come and ask me and I can re-explain it again. Okay. So why do atoms want to gain or lose electrons in the outer orbital? Well, it's very simple. It's just like our octet rule. Um, they want to be stable. Okay, they want to be stable. That's the whole reason why our electrons and our atoms, why they're forming bonds, so that they can be stable. Okay. All right. Now, our next page here, we have, it says atoms in the periodic trend, study guide part 2. Perfect. So 18, substances that touch the stair-step line drawn on the periodic table are called, so I'm going to go back to the periodic table, okay? I'm going to erase this, so I'm going to give you one more second to jot it all down if you need to, or you could just, pause the video as well, that works too. So I'm going to erase this stuff to give us some more space. If I were you, I would 100% write that stuff down, okay? Because on our test, I'm going to allow you to use your blue periodic table on it, okay? So what we have here was substances that touch the stair step here, okay? These substances, and you can see like this black line right here that's making a stair step, so it goes like this, right? That is your stair step. That's what it's talking about here in this question. So all of your, in this case, on this picture, they're all the yellow ones, okay? And on your gray, black and gray copy, this is your light colored gray. I would label these, okay? Because it's going to ask you, and you're going to need to get familiar with the different types of elements, especially for our next unit. So this here, those yellow ones, those are called your metalloids or semi-metals. Okay. The reason why they're called metalloids or semimetals is because they share properties that are both similar to metals and nonmetals. Okay. So on here, majority of your periodic table, all this blue, excuse me, all this blue here, okay, is a different type, okay, and makes up about 80% of the entire periodic table. The blue here, or I believe it's the darkest color gray, these are your metals. All right. These are your metals. Now, the other thing that you need to know is over here, and don't forget our guy hydrogen over here. These guys are all called non-metals. Okay. If you're unsure if it's a non-metal or not, I would probably look for our oxygen here because again, oxygen, that's what we breathe. Okay. It'd be really bad if oxygen was a metal, we'd be breathing it in. So it's a good thing it's a non-metal. Um, so it says, then the question, the elements that touching the stair step, okay, so touching that black line in the stair step, those are known as semi-metals, okay, or metalloids. One more thing before I forget. Hydrogen is your only element on the far left side of the periodic table that is a non-metal. Okay, so on your test, it's going to ask, hey, all the elements in the periodic table in the first group are all what? And if you say are all metals, I'm going to be upset because it's not true. Okay, so they all have one valence electron though. Okay, so make sure you remember that. So substances that touch the stair step, these are called metalloids or non-metals. Okay, so number 19, this is now talking about another trend here. Okay, so we talked a little bit about atomic radius. Okay, now we have to talk about another one. So an atom's ability to attract. Okay, attract is our key word here. Attract electrons is called what? So on your little packet of trends, okay, you have different types of stuff being shown. Okay, one is electronegativity, another is ionization energy, and the other one's atomic radius. Okay, we already talked about this one, so we're going to go back to the front here. So, electronegativity. All right, you have this one on the front page and this one on the second page. We're going to look at the second page one here. Okay, they're both work really well, but I feel like this one just works a little bit better for what I'm going to try to explain. Okay, electronegativity is the atom's ability to attract electrons or the ability to want to take electrons away from another atom. Okay, so again, we have our different group numbers. So just to kind of help you stay on track here, we got group 1, 2, 3, 4, 5, 6, 7, and 8. Okay. So, but we got a lot of different stuff here. All right. What we got going on is remember, the key thing here is what we need to remember is our octet rule. All right, all of our atoms, they want to have 8 valence electrons. Once they have 8 valence electrons, they are stable. Okay, so if we are looking at, let's say, group number 7 here, okay, these guys are all off the chart. Okay, they're, look at it here, right? They're very, very, very high. That means they have very high electronegativity. They want to take electrons, okay? Because if they take electrons, they only need one more electron, okay? If they get one more electron, they're going to start looking and ending up like our noble gases, and that's what they want to get to, okay? So these guys, they have very high electronegativity because they want to take, all right? So your 5, 6, and 7 All right, these guys, they want to take electrons. All right. And what's how many they want to take, it depends. So, depending if we are at 5, 6, or 7, you basically want to be able to get to the difference to 8. Okay, so if you're at 5, you want to gain 3 electrons to get to 8. Okay, so stop, Milo. So now if we look over here on the left side, all the way over here, okay, these guys, they have very low electronegativity, very low values, right? Because all of our group 1, for example, all these ones here, okay, besides hydrogen, all of them, they want to lose electrons. They want to lose them. Okay, so your 1, 2, and 3, they're going to want to lose electrons, okay? Because if they lose electrons, what ends up happening is they fall back into the previous orbital, okay? So, for example, let's say if we're looking at our sodium, sodium has one valence electron. If it loses that one singular electron, it will have the same amount of uh, valence electrons as neon here, which is way over here on the far right side. Neon is element number 10. Okay, so that means it has 8 valence electrons on the outermost orbital and is stable and it is happy. Okay, so now the question becomes, why does group 8 have 0 electronegativity? Okay, so the reasoning why it has 0 electronegativity is because they all have full complete orbitals. Full complete orbitals. Oh, I should say full complete octet. That's probably more accurate. Octet. Okay. So they are already satisfying the octet rule. So that's why they're called the noble gases. So noble gases they are electrically neutral, so that means they have the same number of protons and electrons, and they have a full complete octet. When they have a full complete octet, that means for our noble gases only, they are unreactive. Unreactive. Okay. So electronegativity is again here. And an atom's ability to attract electrons is called electronegativity. Okay, they're going to want to take electrons from other atoms. Okay, so number 20, it says a substance that has very high electronegativity values will most likely be what type of element. So if it's asking for a type, it's asking, is it going to be a metal, um, metalloid, or non-metal? Okay. So, oh geez, I made a mistake. Hold on. So this isn't non-metals. That's my fault. This is semi-metals. Okay. So going back to 20, a substance that has very high electronegativity will most likely be what type of element? Okay, so going to your periodic table, right? Yeah, your periodic table. So I would look at this and try to remember the colors and what they mean and everything, okay? Then we're going to look at our trends here, okay? So if you looked and if you remember, these ones on the far right side, okay, these ones over here, they have the highest value of electronegativity. So those types of elements are called your non-metals. Okay. All right. Now, 21. Identify the number of valence electrons from each of the following elements. Okay, so this process, once you get the hang of it, is pretty easy. Okay, it just takes a little bit of practice. So remember, valence electrons here, these are the electrons, the outermost orbitals of our atoms. Okay, so going back to our periodic table, well, first let's take one with us. All right, so you see this number here, it says 14. That is your atomic number. Okay, so we're looking for element number 14. So, element number 14, let me erase this. Element number 14 is this right here. Okay, so element number 14 is silicon. Now, what you are going to want to do, okay, to figure out how many valence electrons, okay, you need to look first. All right. Now, if you say that silicon has 14 valence electrons, that is incorrect. That is not the number of valence electrons. That's the total number of electrons and the total number of protons, but not valence electrons. Okay. Now, the valence electrons are coming from your group numbers. So if you guys are all good noodles, which I know that you guys are, you would have circled it and labeled it on your periodic table. Your group numbers are directly above, all right, not the charges, the number that's right above it. So here, okay, that's a group number. So all of your elements that are in that vertical column, so including carbon all the way through lead here, these guys all have 4 valence electrons. So what you're going to do is you're going to go back to here and find silicon and then write 4 next to it. Okay. Now I'm only going to do a few of these because I want you to practice them a little bit as well. And if you don't want to, well, I guess that's your choice. And I guess you might be able to look at your answer key on Google Classroom. So the next one I'm going to show you guys is boron. Okay, boron is element number 5. Okay, so boron is element number 5 here. Okay, and now the valence electrons again is not 5. Okay, it is the group number. So your group number is 3. So boron is going to have three valence electrons. Okay. Now let's go down. All right, I'm gonna save these 4 for you guys. I want you to try, and you can check it out in your notes, okay, or on the Google Classroom key. So what we're gonna do next is element number 56, barium. So we're gonna find 56. So I'll look, well, 51, 52, 53, 54. Oh, we probably got to go over here. Oh, there it is, cesium and barium. 56 is barium, which is right here. Okay. Then what you're going to go and do is you're going to go all the way up to here. This too. That tells you how many valence electrons it has. So barium will have 2 valence electrons. Okay. Now, the other one that I want to go over with you is helium, which is element number 2. Okay, so I saw this on your guys' test quite a bit. So, if we look for helium on our periodic table, helium is over here in the top right. Okay, so I know what you're thinking already. Well, helium, according to our trends and what we've been talking about, helium is going to have 8 valence electrons because it's in group 8, right? No. So helium is the only one that's not going to have 8. Not 8. Now, all the others ones will, yes. Okay, so all the other noble gases will have 8 besides helium. So this 8 applies to everything down here, okay, and below. So if it doesn't have 8, how many does it really have? So if it doesn't have 8, it can only have 2. Okay. Now the reasoning why it only has 2, if we look here at our periodic table, in our first period, we only have 2 boxes and we only have 2 electrons that we can fit into it. Okay. Now, it's not about how many electrons are there, it's talking about stability and how much are full. Okay. So, in our first period, helium has 2 electrons, 2 valence electrons, and that fills up the full orbital. So that means helium will only have 2 valence electrons, or 2 electrons in general. Okay. If that doesn't make sense, please let me know, and we can talk about it later. Okay. So now 22. All right. We have the 3 different kinds of trends that we've been talking about. So we've been talking about 2 of them already. We talked about atomic radius, talked about electronegativity. Okay. So let's start with atomic radius. All right. Atomic radius is the only trend on here that's different from the other 2. Okay. So you can tell what it is by simply just looking at the arrows. If you're unsure, well, let's look at our packet. So if we go to our packet and we flip all the way to the very back here, okay, this shows our obvious trend. All right. If we're going from the right side to the left side and from the top to the bottom, the overall trend from helium all the way to cesium here is that from the top right to the bottom left, it is increasing. Okay. The atomic radius is going to increase from the top right to the bottom left. So we would go back to our questions here. We're going to find the one that looks like, and so atomic radius is going to be our second one. Okay. So we got atomic radius. Now we have 2 more. All right. We have electronegativity and ionization energy. So electronegativity, remember, it's an atom's attraction towards another atom's electrons. Okay. So remember, if we're talking about our noble gases that already have 8 valence electrons, they're going to be unreactive. They're not going to be attracted to other electrons. So what this X representing is this whole column, or column number 8. That's like, hey, we're not talking about that one. So electronegativity is going to go right here. Okay, electronegativity. Now, the other one that we got to talk about is ionization energy. All right, so yeah, well, process of elimination. That means I guess ionization goes over here. Okay, but let me explain what it is. Okay, if electronegativity is talking about an atom's likelihood to take away an electron, or the attraction it has towards another atom's electrons, they just don't do it for free. Everything has a cost, right? I mean, you have to pay for your bag of chips or at the K&A. Well, our atoms have to pay energy in order to take away electrons from another atom. Okay, so we have to go and we're going to look at our periodic trend of ionization energy here. Okay, what we're looking at is how much it costs to take away an electron from an atom. All right, so to help us, let's see which one's better. We'll start here. So what we have here in our first column, so column number 1, or group 1, right? We have hydrogen, lithium. You know what? That's going to be confusing. Let me go back. All right, so And the red column here, right? This is our group 1, 2, 3, 4, 5, 6, 7 is for yellow, and 8. Okay. As we're going from the bottom to the top and from left to the right, ionization energy is going to increase. So it's going to be more expensive to take away electrons from our noble gases. Okay. So super duper expensive, like lots of energy. Okay. Whereas down here for our rubidium in the bottom left side, it's going to be very cheap. Okay. Now, the reasoning for this is a few things. Now, our group 1 elements that it's in the red, those guys, they already have one valence electron, right? What they want to do is they want to lose it. They want to get rid of it, okay? Well, these guys, our yellow guys over here, our group 7, they're going to want to gain it, okay? So they are going to pay that cheapness of an electron to take away that electron from like our group 1 elements. Okay. Now, the thing is, there has been times where some atoms have taken away or shared electrons with our noble gases. It's not as likely, but it can happen. The only guy or only element to do that, or that's known to do that, is fluorine. Okay, because its electronegativity value is so high that it's likely to take away or share electrons with xenon. All right, so fun fact for you. You're not going to need to know that for the test. Okay, but the thing is, what I'm trying to get to you or let you guys know that our noble gases, they don't want to lose electrons. They have 8 already. Why are they going to try to get rid of them, right? So they don't want to. So it's going to be very expensive to take away electrons from them. Okay. The other reason is if we look at atomic radius, okay, our atomic radius here, if we look at the different sizes, okay, our helium, our helium atom way over here is really small, but our cesium atom on the opposite side is very large, okay? So what's happening here, as we are going from the left to the right on our periodic table, we are adding protons, neutrons, and electrons, so that's taking up space. So that's part of the reason why they are getting smaller as we're moving from the left to the right. Now, the other reasoning is when you have protons and electrons in a small closed area, they have these electric currents, all right? Like think of it as like a pole of magnets that are going to be pulling towards each other. And when they do that, it's shrinking the atom, okay? So helium is so small that those protons and electrons are so tightly knit that it would be crazy expensive for it for any type of other atom to try to take away an electron from helium. Okay, so if we're looking at here, right, helium, which is this one here, is what almost 2,400. We can call that dollars to make it easier for us to think about. Right, so that'd be like $2,400, which is crazy expensive. Or we could take an electron from francium down here that's say let's about I don't know $100. So which would you rather pay to complete your octet if you were a like let's say a fluorine atom, right? Would you want to pay $2,400 or $100 in order to take that one electron away? Okay. So ionization energy here is all about cost. How much energy is it going to cost in order to take one electron away? Okay. All right. Hopefully that makes sense for these. If it doesn't, like I said, please come and talk to me. I'm more than willing to help you. All right. Now, for 23, And on your test, it's all these different kinds of questions are just asking you to really just take this stuff and apply it. All right. So we have for 23, it says put the following elements in order of increasing electronegativity. So again, your numbers that are down low here, these are your atomic numbers. All right. What I would do if I were you is first, I would find them on your periodic table. So let's start with chlorine, which is 17. Erase this. So chlorine is element 17, which is right here. Then we have sodium, which is element 11, which is right here. Then we have element 15, phosphorus, which is right here. And then we have element 19, which is potassium, which is right here. Okay, so now you kind of have an idea and understanding where they are. Now what you need to do is you need to find them on your packet, and you should be able to figure out where they go. So if you go to the electronegativities here, you got chlorine, you got phosphorus, you got sodium, you have potassium here. Okay, so ranking them from the lowest or increasing electronegativity, so from the lowest to highest. So your lowest would be potassium, and then it would be sodium, and then it would be phosphorus, and then it would be chlorine. Okay, so that's all that you're doing. You're finding them and you're relating the trend to it. Okay, so that's what we're going to be doing for 23. You're also going to be doing that basically the same thing as that for 29, 30, and 31. Okay, so rank, right? Rank, so put in order the following elements from the highest electronegativity to the lowest. All right, so you're ranking them 1 to 5. And remember, we got argon here, so it's a trick question. Okay. Then it says, referring to 29, rank the elements from highest ionization energy, so highest energy or cost, to the lowest. Okay. And then the same thing for 31, referring to 29, rank the elements from the largest radius, so the bigger the ball, the bigger the radius, to the smallest. Okay, so you're just using your packet and your periodic table in order to place those from the lowest to highest. Okay, just apply it. That's all that we're asking here. Okay, so I will have to have you guys do that on your own, all right, so you can kind of figure it out, all right? Now, what is the difference between a group and a period? Okay, now we talked about this quite a bit. So a group here, group is your vertical columns, those are going up and down, and your periods are your horizontal rows going left to right. So groups is your columns, your periods are your rows. Okay. So, number 25, which group or family on the periodic table is the most stable? Okay, so most stable, or if you think of it, which one is unreactive? Okay, because if it's unreactive, that means it's stable. They're not going to try to gain or take away electrons. Okay, so the group or family is group 8, which is your noble gases. Okay, why? Because they have 8 valence electrons. Okay, so again, 8 valence electrons, that's our octet rule. I think that's the third or fourth time we talked about it just in this video. Okay. Now, it says 26, draw the Lewis dot structure for each element. So if you were able to draw, excuse me, if you were able to draw or figure out how many valence electrons the, um, like each atom has, okay, you should be able to figure out the Lewis dot structures as well, okay? And again, I'm only going to do the first box of four, and you guys can figure out the other four, all right? So if we're looking at lithium, let me go back to our periodic table. Lithium is over here, okay? It's going to have one, right? That's one valence electron. So if it has one valence electron, going to have one Lewis dot, okay? Now let's look at sulfur. Sulfur is element number 16, so we're going to find 16 on our periodic table, which is right here, okay? If you look here, again, we're looking at our group number, which is this, which is 6. It'll have 6 valence electrons, okay? So how do you fill these in? So what I want you guys to do, I want you to get into practice with it, okay? Think of it as like a compass. So I have north, east, south, and west. That's the kind of direction of how we want to do it, all right? So you're going to start with north. So right above it, you're going to go 1, and you're going to go clockwise. So I got 1, 2, 3, 4. Now I need to make 6 in total, okay? Now I'm going to start filling them in from the top again, making pairs. So now I got another one here for 5, and then another one here for 6, okay? Now, fluorine is number 9. So fluorine is here, and it's going to be very similar to sulfur, okay? Just like we said, fluorine is going to be in the group here of 7. So it's going to have 7 valence electrons. So we're going to go 1, 2, 3, 4. Okay, then we're going to go again around for 5, 6, and 7. Okay. Boron is element number 5. So we're going to find boron, which is right here. You're going to find the group number that it's in, which is element number, group 3. So boron's going to have 3 valence electrons. So it'll have, let me do it in a different color so we can see the difference. 1, 2, and 3. Okay. Now I want you to do those 4 by your own, and then you can check your notes or check what you call it, the study guide key. Okay. So 27. As you go down a group, so down a vertical column, what happens to the value of the ionization energy, right? So what happens to the cost? So we got to look at our picture here. All right, as we are going, let me erase all this. As you're going down the group, what happens to the value, right? So if you're going down here, right, the value of the ionization energy is it decreases. Okay. So decreases. As you go across, so across a period, so our rows from left to right, what happens to the radius of the atoms? Okay, so we're going to go all the way back over. So we're going from left to right, okay? So if you want to look here, going from the left to the right, what happens to the size of the ball? Okay? The size of the ball is also decreases. So decreases. Okay? So you should be able to figure out 29, 30, and 31 with some practice. Now, I want to talk to you about this real quick, okay? Because this here, a lot of us got it wrong in our test, okay? So, like I said before, let's look at helium, okay? Your atomic number tells you a lot of information. So, the very first thing that you see when you see atomic number, okay, your atomic number tells you a few things. Right away, it tells you how many protons it has. So your atomic number 2, what you want to write as soon as you see it is 2 protons. Okay? Now, the center part that is like a dark shaded gray, that is your nucleus of your atom. Okay? What we need to get to is that center part needs to equal a total of 4. All right? That's as our atomic mass. Okay? Remember, your atomic mass is your protons plus your neutrons. Okay, so if I already have 2 protons, how many more do I need to get to a total of 4? Okay, that means we need to get 2 more neutrons in that center. Okay, if you can't think of it that way, that's okay. What we can do is we'll take our atomic mass, right, that number, we'll subtract it from your atomic number. And when you do that, that's where you get your total number of neutrons. Okay, so it's not adding. You're not going to take your atomic mass and place it where the neutrons is because that's incorrect, right? If you decided, you know what, I'm not going to listen to Mr. Buchanan, I'm going to put mass of 4 right where neutrons is anyways, I'm going to mark you wrong, okay? Because what that tells me is that your atomic mass is not 4. What that means is that you are basically putting your 4 and your 2 together and making it 6, and that's wrong, okay? Don't put mass 4 where neutrons is. It has to equal 4, okay? Now, this is where the tricky part comes in on your periodic table, okay? How do we fill in our electrons? So these are all neutral elements, okay? Your protons and electrons need to be the same. Okay, so what we need to do is we need to have a total of 2 electrons. So when you're looking at your periodic table here, okay, when you're looking at your periodic table, each period represents 1 orbital. Okay, so your first period is your first orbital, and helium falls into that first period. Okay, think of it as if we are at a seats of a concert. All right, we're at this periodic table of elements concert, and we got people lining up at the door over here. Okay, what we need to do is no matter what at a concert, you always are filling the first row first. Okay, so in this case, that means we're filling in at our first period. So you're always going to start at hydrogen no matter what. Then you're going to go from left to right. So we have 2 boxes. Okay, we got 1, 2. That means we can only fit 2 electrons in our first orbital. So we're going to go 1 and 2. Okay, now it should look something like this when you're done. Let's do oxygen here. All right. So remember, your very first thing that you should see or should do, right? You got your atomic number. That's going to be your protons and your electrons. And your mass is your protons plus neutrons, and that is your total. Your total is your mass here. Okay. So atomic number 8. So the very first thing you do when you see that, you're going to write 8 for the number of protons. Okay. If you're unsure now what to do, okay, what you need to do is you need to take your mass number, 16, you're going to subtract it from 8. Okay, so you're taking your mass and you're subtracting it from your atomic number. When you do, you get 8 minus 8, or 16 minus 8, you get 8 neutrons. You're going to take that new number and you're going to place it next to your n. So now you should have it correct. You know if you did it right, if when you add those two numbers up, they equal 16, okay? Now, going back to your periodic table for oxygen, all right, so we're filling out our rows here. In your first period, no matter what, you can only fit 2 electrons in it, no matter what, okay? Because again, we only have it 2 squares. That means we only have 2 electrons that we can fit in that first period, which is our first orbital, our first ring from the center part of our nucleus, okay? So, that's the first step. So we're going to go 1, oops, we're going to go 1, then we're going to go 2. Okay, now we need to have a total of 8 electrons. Right now we have 2. So that tells you right now we need to fill up 6 more electrons in the second orbital, okay? Because 8 plus, or 6 plus 2 gets you 8. If you're unsure, go back to your periodic table. We filled up our first period already, so that's good. Now, we look here, we need to get to oxygen, which is way over here, okay? We start here now, we got 1, 2, 3, 4, 5, 6 more spots, or 6 more steps, or seats available to get to oxygen. So, we are going to fill up 1, 2, 3, 4, 5, and 6. So that's what it should look like, okay? Now, aluminum, again, it tells you how many protons and electrons is your atomic number. So I'm going to write 13 for protons. Your mass, 27 minus 13, okay? 7 minus 3 is 4, 2 minus 1 is 1, so you should have 14 neutrons, okay? Then again, now we're going to start filling in our orbitals again. So in the first circle, just like how we've been doing in our first orbital, we only fill in 2 electrons, okay? Now, we need to get at least 11 more electrons in order to get to 13, okay? But according to our periodic table, if we look here, there is not 13 boxes that are present in our second period, okay? So there is not 13. So there are actually 1, 2, 3, 4, 5, 6, 7, 8 boxes available, which means we fill in 8 electrons in the second orbital. So 1, 2, 3, 4, 5, 6, 7, and 8. Okay, now, if you were to count up all the electrons that are present, we have 8 in the second, 2 in the first. That's a total of 10, so that means we need to have 3 more. All right, and there's no more space available in the first orbital or the second orbital, so that means we've got to place them in the third orbital. So 1, 2, and 3. Okay. Chlorine is going to be very similar to aluminum over here. Chlorine is atomic number 17 and has 17 protons. If you do 35 minus 17, you will get 18 neutrons. Okay, so you're going to write 18 next to the N. Now, just like what we did for aluminum, you can only fit, remember, 2 electrons. 2 electrons in your first orbital. How many can you fit in your second orbital? You can only fit a total of 8. So we got 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so now we're at a total of 10 electrons, right? So if you add up all the dots that are present in our chlorine, we have 10. We need to get to 17. So we need to add 7 more in our third orbital. So this would be 3, 4, 5, 6, and 7. Okay, so that's how you fill it out. And if you're unsure, again, you reference your periodic table here. Okay, here it is. What we did, we filled up our first period. So we did 1, 2, and then we filled up our second period, our second orbital of 1, 2, 3, 4, 5, 6, 7, 8. Then we filled up our third period, which is a third orbital, until we get to chlorine. So 1, 2, 3, 4, 5, 6, and 7. Okay? So hopefully this makes a little bit more sense. If you have any questions, please stop by my room, okay? I'm going to be staying late because I'm going to be doing a lot of work for your classes and my classes. So please stop on by whenever you did or whenever you do. Um, and if you make it to the end of the video, give yourself a pat on the back because I know it's very long and dragging and can be very boring. But I do appreciate it that you guys took the time to actually watch this and pay attention to it the whole way through. Okay, and again, this is all for you guys. Okay, so if you need help, please, please, please come on by, stop by whenever. Okay, if you have any questions, please let me know. Okay, all right, Mr. Buchanan out.